Hello everyone, welcome to the 22nd episode of the series. In this video, we'll talk about subsets and subspaces. So recall that the solution set to a system of linear equations can be an empty set if the system is inconsistent, and if the system is consistent, then it can be a point, a line, a plane, or perhaps a shape in higher dimension. So this is a very powerful classification because the shape is determined by its dimension, which we defined as the number of parameters used to describe the solution set. So now in this episode, we're going to focus on shapes of solutions for homogeneous systems of linear equations. So recall that we call a system of linear equations homogeneous if all the constant terms are zero. In other words, the corresponding matrix equation is A times the vector of variables equals the zero vector. So when the system of linear equations is homogeneous, we can still have all the shapes possible for the set of solutions, but we can't have the empty set anymore because the zero vector is always, a solution. So there is always at least one solution. So the solution set cannot be empty. So why are we focusing on homogeneous systems? Because the properties are nicer, and the solution set to a general system of linear equation is related to the solution set to another homogeneous system of linear equations. So the goal is to define and study these general planar shapes through the origin. Now, because we cannot view things outside of 3 dimensions, we are going to uh, deal with vectors of height 4 or more with the following strategy. We're going to find a few important properties that characterize these planar shapes, and then we're going to use those properties as a general definition. So, in other words, what properties distinguish the solution sets to homogeneous systems of linear equations to all the other shapes in Rn. So first, we're going to introduce some new terminology. We're going to start with the definition of subsets. So suppose A is a set and B is another set whose elements are all elements of A. Then we say that B is a subset of A. We can also say that A contains B, or A is a superset of B. In other words, if B is a subset of A, every element of B has to be an element of A, or if an element belongs to B, it has to belong to A as well. Let's look at some examples. So in the first one, this set with the two elements 1 and 3 is obviously a subset of 1 to 3 because this set has two elements 1 and 3, and they both belong to this set of 3 elements as well. The same set is also a subset of the set of real numbers R because this R contains every possible real numbers, and 1 and 3 are real numbers. Any set V consisting of any collection of vectors of height 2 is a subset of R2, and the set R2 itself is a subset of R2 as well, which brings us to a very important point that every set is a subset of itself. Do note that the set R2 is not a subset of R3 because the lengths of the vectors are different. In other words, a vector of height 2 is not a vector of height 3. And this set 1, 2 over 5 is not the subset of integers because 2 over 5 is not an integer. Okay, so let's look at another definition. So suppose we have a subset S of Rn. We say that S is closed under addition if for any two vectors in S, their sum is also in S. So every time you have a pair of vectors in the subset S, the sum always belongs to S. So if that happens, we say that S is closed under addition. Now, similarly, we define closure under scalar multiplication. So we say that S is closed under scalar multiplication if for every vector in S and every scalar in the set of real numbers, the product is also in the set S. So let's look at an exercise. So we're given a non-empty subset of Rn, which is closed under scalar multiplication. So we have to show that it has to contain the zero vector. So because this set is non-empty, there has to be at least one vector in it. And because it is closed under scalar multiplication, we can multiply it by any scalar, and this product of the scalar and the vector has to be an S as well. So I can just choose to multiply by c equal to 0, and when we do that, we end up getting the zero vector, and therefore we have shown that the zero vector belongs to the set S. Okay, so now we come to our first theorem. So we're going to talk about properties of solution sets to homogeneous systems of linear equations. So let V be a solution set to a homogeneous system of equations in n variables. Then V is a subset of Rn, that is the elements of V are n vectors. V contains the zero vector, and it is closed under addition, and it is closed under scalar multiplication. So just to recap, the solution set to a homogeneous system of linear equations is going to be a subset of Rn that contains the zero vector and is closed under scalar multiplication and addition of vectors. So there's a little bit of overlap in these properties. For example, we don't really need this property of V containing the zero vector, because we just showed on the last slide that closure under scalar multiplication actually implies the containment of zero vector. So we can just forget about that. Okay, so let's look at another definition. So a subspace of Rn is a non-empty subset of Rn, which is closed under addition and scalar multiplication. So it satisfies three properties. It has to be non-empty, and it has to be closed under addition and scalar multiplication. So here are some basic examples. The first one is due to theorem 1 that we saw on the previous slide, and that is that the solution set to a homogeneous system of linear equations is a subspace of Rn. So we want it to be non-empty, and we know that the solution set to a homogeneous system of linear equations are non-empty, and we want it to be closed under addition and scalar multiplication, and that's exactly the content of theorem 1. And then some of the other examples of subspaces are, the origin, or a line through the origin, or a plane through the origin, or this set of two vectors whose entries sum to 0. You can check that this is closed under addition and scalar multiplication. Okay, so let's move on to the next thing on the menu, that is the definition of the kernel of a matrix. So if A is an m by n matrix, then the kernel of this matrix A is the set of all vectors that satisfy A times B equal to the zero vector. The kernel is also called the null space of A sometimes. But note that the kernel of A, just by definition, is exactly the same as the solution set to this homogeneous system of linear equations. And because it's the solution set to a homogeneous system of linear equations, by theorem 1, we get that the kernel of any m by n matrix is a subspace of Rn. So let's look at an exercise to get ourselves a little bit more acquainted with the concept of kernel. So we're given this 2 by 2 matrix, and we have to determine whether these vectors are in the kernel of A or not. So it's not very hard. All we have to do is we have to multiply this matrix with these vectors, and if the result ends up being the zero vector, then then the vector in question is in the kernel indeed, and if not, then it's not. So we multiply our matrix A to 2 minus 2, and we get 4 minus 4. We multiply this matrix A to 2, 2, and we get 0, 0. And we multiply this matrix to 0, 0, and we of course get 0, 0. So we conclude that the vectors 2, 2, and 0, 0 are in the kernel, but the vector 2 minus 2 is not. Okay, so for another example of a subspace in Rn, we turn to the definition of the lambda eigenspace of a matrix. So if A is a square matrix and lambda is a number, then the lambda eigenspace of A, denoted by E lambda of A, is the set of all lambda eigenvectors along with the zero vector. In other words, E lambda of A is the collection of all vectors in Rn, including 0, such that AV is lambda V. So just as a clarification, 0 is not an eigenvector, but it is a part of a lambda eigenspace. Now, it is important to remember that the lambda eigenspace of A can also be described as the kernel of the matrix A minus lambda I and the solution set of the equation AV equal to lambda V. So now, because it is the kernel of a matrix, and because by theorem 2, kernels are subspaces of Rn, we conclude that lambda eigenspace of any square matrix is also a subspace of Rn. So far, all of our subspaces have been examples of a particular kind. They're solutions to a particular homogeneous system of linear equation. So let's look at another example that is not in the same league as them. So that brings me to the definition of the image of a matrix. So if A is a matrix, then its image is the collection of all vectors V that can be written as V equal to AW for some vector V in Rn. In other words, you take all possible vectors W in Rn and you multiply A to all of them, and the collection of all outputs is going to be the image of A. And it ends up being a fact, as I promised, that the image of any m by n matrix is going to be a subspace of Rm. So let's finish this episode with an exercise. So we're given a 3 by 2 matrix A, and we want to verify whether these three vectors V1 and V2 are in the image of A. So determining whether a vector in the image of A is the same as solving the following systems. So for the first one, you just multiply the matrix A with a vector of variables x, y, and you set it equal to 0, 1, 2. And in the second case, you set it equal to 1, 0, 0. These are my vectors V1 and V2. And then if this equation was to be true, in other words, if there was values of x and y for which this equation holds true, then we would say that these vectors V1 or V2 are in the image of A. So this just reduces to solving these linear systems, and you guys are very well aware of how to do that. So I'm just going to jump to the answer. When you solve them, you will see that the first system has the solution 1, 1, and the second system has no solution. So we conclude that V1 is in the image of the matrix A, but V2 is not. And with this, I would like to end this episode. I will see you guys soon. Up until then, happy learning.